you very much for inviting me to this workshop. And I'm happy to talk in this workshop because Calabi-Yau manifold is my most favorite manifold. And basically I talk about some notion of, sometimes I omit Quasi-BPS category. And there are several motivations of considering such a category. And the first one is about admissible geometry that is Donaldson-Thomas invariant. So this is the motivation. And also it's Donaldson-Thomas invariant is some integer or rational number, but I'd like to consider its certain categorification. And the second one is, so this is closely related to physics, but the second one is closely related to the classical algebraic geometry. And I talk about the motivation with singular homomorphic symplectic varieties. And also this is also related to like the geometric Lagrange. And also its classical limit, which is certain duality between certain Higgs bundles. But so today I only talk about 4 and 2, and the third one is still work in progress, and maybe I don't talk it today. But I just want to say that this is also related to such research subject. So first I explain about Donaldson-Thomas invariant in somewhat informal way. So this is defined from Calabi-Yau threefold, and also a choice of some data like Chern character or stability condition. So the given x, so this is Calabi-Yau threefold. So basically I'm interested in the moduli space of semistable object determined from x. That is, from x we can define certain space mxv. So this is moduli space of semistable objects. In the bounded derived category of coherent sheaves on X. But in order to give a nice space, we have to, so this fix some Chern character, so V is a fixed Chern character. And also, I also need to fix some stability condition. Which I assume to be somewhat generic. So my motivation is to understand the geometry of this moduli space. So the whole hope is that give certain geometric understanding of such moduli space. This is because in classical algebraic geometry, so the considering such moduli space is a source of many interesting varieties. For example, so this is a Calabi-Yau threefold, but in the two-dimensional case, so this is a KC surface. So when S is a KC surface, and if you take V to be element of the nuclear lattice, and if you take V to be somewhat primitive, that is, it is not divisible by positive integer bigger than 1. And in that case, the this moduli space, so this has a very nice and beautiful structure. So this is in fact holomorphic symplectic manifold. So this is due to Mukai. Moreover, so the deformation type of this manifold is well studied, and in fact, this is also deformation equivalent to the Hilbert scheme of points. And in fact, so there is a issue about the study of higher dimensional homomorphic symplectic manifold, and in general, this is very difficult to construct examples of homomorphic symplectic manifold, and there are not so many examples are known except this case. And I'd like to see something similar geometric structure of this moduli space on Calabi-Yau threefold. But in general, so if you consider such a moduli space in higher dimension, so the issue is that so it has quite highly complicated singularities, highly singular. So singular means that so it may not be reduced, it may not be reducible, so it is out of the control beyond the in the usual singularities in birational geometry. Also, in the case of KC surface, we get something also the manifold which has trivial canonical class. But in the Calabi-Yau threefold case, so in general, so this moduli space may not be Calabi-Yau, something like Fano or general type, if when it becomes smooth by accident. And when I say geometric, so this means that so a bit not precise, because so this moduli space is forgetting some important structures which happened from the moduli theory. And in fact, so geometric means that I should say this is with some structures. So I explain about this structure later, but roughly speaking, so Donaldson-Thomas invariant is a certain numerical shadow of this moduli space, which keeps track of these forgotten structures. Donaldson-Thomas invariant, or sometimes this is also called BPS invariant. So this is a numerical shadow of this moduli space. With structures. So this structure is that so there are two structures which are forgotten. The first structure is that we are forgetting some stacky structures. So a priori, if you consider moduli space, so usually, so if there are some non-trivial automatisms, then the moduli space is not a usual scheme, but it is some stack. And second one is that we also have some deformation obstruction theory of this moduli space, which contributes to this highly singular structures. So this is a derived structures. One can package these structures by the following diagram. So let's write mxv just by m for simplicity. So in fact, so this is a certain GIT quotient of some stack. That is, in fact, there is a natural moduli stack, which I denote by cardi m. So this is a scheme or algebraic space. But this is a moduli stack. So something like variety with group action, and this M appears by taking the honest quotient by these group actions. So from this step, we forget the automoism of the semistable object. So this is, remember automoism of this moduli space. So this keeps track of these first structures. And the second derived structure is that it also admits certain natural closed immersion. So this is a derived stack, derived moduli stack. So roughly speaking, so it remembers the deformation obstruction theory of the corresponding moduli theory. So this is the second structure which we should keep track of. So then the Donaldson-Thomas invariant is constructed from this derived stack. So if you know about, for example, Gromov-Witten theory, so we have also similar picture. For example, you can consider the moduli stack of stable maps. And then this is just a coarse moduli space. And in that case, we have also derived structures, but usually we don't consider derived structure, but so-called perfect obstruction theory of this stack. So this is nothing but the tangent complex of this derived stack. Okay, so that's right. Right. So then the Donaldson-Thomas invariant is, so this is a certain nice invariant which keeps track of both A and B, and I'd write that omega V. So this is defined to be Euler characteristic of the some cohomology theory is respect to some power sheaves. And this phi m is, so yes, so it requires some more time to explain its detailed definition, but roughly speaking, this is defined by taking the first perverse cohomology of certain perverse sheaf on this stack. M. And so this is some perverse sheaf on this moduli stack, and that is called Joyce vanishing cycle complex. Joyce vanishing cycle. And in defining this such a complex, we need this derived structure. But more precisely, it also has some so-called some shifted symplectic structure. In the case of KC surface, we have the usual notion of symplectic structure, but on here, so it is equipped with so-called -1 shifted symplectic structure. And together with some more data that is called orientation data, which I don't explain today, which also then we can define such perverse sheaf on this moduli stack, and then push forward to here, and then take first perverse cohomology. So this phi m is called BPS sheaf. Which was introduced in the case of quiver with potential by Davison and Meinhardt, and in this global case, this was Davison, Meinhardt, and also myself in the Calabi-Yau case. And this construction was also used to define Gobachman buffer invariant on Calabi-Yau by using this cohomology theory. So this is some nice invariant, and so this is similar to the Euler characteristic of this usual Euler characteristic of this moduli space, but it also keep track of these two structures. But here is one crucial difference from the Gromov-Witten theory. In the Gromov-Witten theory, so if you consider moduli stack, then this is always Doyle-Mumford stack. So then you can construct a virtual fundamental class using this derived structure. Then you define the invariant by taking the integration of the virtual fundamental class. But in the Donaldson-Thomas theory, the one difficulty is that so this stack is not necessarily Doyle-Mumford, and in many cases, so this is Artin stack. So that means that the automatism group of such stack is usually not finite. And in that case, so there is no natural virtual fundamental class on this stack. But in some cases, so we can ignore such an issue that, for example, if in the case that there is only a stable object of this moduli space, then we can ignore the first issue. As a remark, the first remark is that when semi-stable equals stable case, so then in that case, we can ignore the first issue because this moduli stack is essentially, the map pi is essentially almost isomorphic up to some trivial automatisms. So that is, in that case, we can essentially ignore the can be sucky issue. And in that case, so this invariant is also written as the integration of the usual virtual fundamental class. And so this was the original definition by Richard Thomas of defining Donaldson-Thomas invariant. So this is similar to the usual construction of the Gromov-Witten theory. But as I said, so yes. Also, so this condition is checked by some condition of this numerical class V. For example, when V is like 1, 0, minus beta, and minus chi, so that is in H0 plus, H2 plus, H4 plus, H6. So in that case, for some suitable choice of stability condition, so such a moduli space is some moduli space of curves inside Calabi-Yau threefold. And in that case, so this semi-stable equals stable happens, and so such an invariant basically counts curves inside Calabi-Yau threefold, and there is a famous relationship Gromov-Witten invariant. That is so-called MNOP conjecture, which was proven by John Pardon last year. However, so in many cases, it happens that semi-stable is not equal to stable. For example, this happens when this V is some multiple of some primitive Chern characters. So another remark. So let's say, so this case is I take first vector. So this is the rank of the sheaf. So this is just rank 1 sheaf, and the object which contributes to this moduli space is like ideal sheaves of such a curves. But if you just consider V equal like 0, 0, beta, and chi, then it happens that this may be some multiple of some other vectors. And in that case, so it sometimes happens that semi-stable is not equal to stable in general. And if this equality does not hold, we have to consider this definition. So, but nevertheless, we can consider anyway this invariant. So the surprising fact about this invariant is that So this is independent of the choice of the additional parameter chi. So this was observed by myself many years ago, and that was conjecture at the time. And I knew that this follows from several conjectures like chromophytem, PT correspondence, and also the so-called the Bachmann buffer finiteness of chromophytem invariant, and also the combining these conjectures at that time, and also the Wolff-Cauchy argument. The chi independence follows. But so these conjectures are not now proven. So in fact, so this is now theorem by combining these big results. But still, this is a mysterious phenomenon. We don't still have the purely sheaf-theoretic proof for this chi independence. Anyway, so because this chi independent, we can drop chi from this notation, and this is nothing but the genus equals 0 Bachmann buffer invariant. And this invariant plays a important role in considering the wall crossing of this curve counting invariant. Yes?
Would you write the formula for virtual dimension?
Virtual dimension is 0.
Yeah. So in terms of V.
In terms of, sorry? In terms of?
V, chi vector.
Yes, for any V. So this is always 0 dimensional. Virtual dimension.
Yes.
Virtual dimension is always 0 for the Donaldson-Thomas invariants on Calabi-Yau seafold.
So I'm just asking you in terms of those, components of vector.
So you can consider like chi of V and V. So this is basically virtual dimension, but for Calabi-Yau seafold, this is always 0. So this is different. Yeah, sorry, but even in the Gromf-Witten theory, for Calabi-Yau seafold, this is as virtual dimension 0, right?
Right.
Yeah. In the Calabi-Yau seafold case, so this is always virtual dimension 0. So now, I'm going to talk about some main motivation. As I said, I want to give some more geometric understanding of this moduli space of semistable objects, which somewhat keeps track of these A and B. So, but before going into that, let's recall the following observations. So, starting from some Y, so this is smooth projective variety. So then we can associate the number just the Euler topological Euler characteristic. Of course, so this is Euler characteristic of some singular cohomology. So this is taking Euler number. And in defining Euler number, it is enough to consider it as a G2 graded vector space. So from Y, we can associate also this cohomology theory. And we can also associate the boundary derived category of coherent sheaves on Y. It remembers the G2 graded vector space of this singular cohomology. For example, we can take either topological case theory or periodic cyclic cohomology or so on. So there are some invariant defined from the DG category. So this is now DG category. And in fact, so this is very nice DG category that is smooth and proper. So I just give some brief definition about what is smooth and proper DG category. Let's say DG category. So this is called smooth. If so, the so-called diagonal, the tensor sorry, DG category, or maybe I should say C linear. DG category D is smooth if the diagonal D tensor D of module. So there are natural module over this product, so this is perfect. So you can see that, you can imagine that if you consider the diagonal module over the product, then this is perfect. And this is called proper if the, for each object, even it's, so this is finite dimensional. In particular, for each session-to degree, so this becomes 0. So if you have some DG category satisfying this smooth and proper condition, it satisfies several nice property. For example, like the existence of a strong generator, existence of safe functors, and so on. So this is regarded as certain very nice space in some non-commutative geometry. That is, so that we may want to consider some DG category satisfying some nice condition as if it is some space. And if the DG category satisfies such a condition, we may say that this is some nice space. I'd like to apply this observation for the Donaldson-Thomas theory. That is, starting from this derived stack. So I'd like to give some geometric understanding of this moduli space or moduli stack. But of course, this derived stack is out of control in the classical geometry. So this is just some functor from some infinity categories. But from here, we can associate the integer. So that is a BPS number, or Donaldson-Thomas invariant. And from this definition, so this is some Euler characteristic of some cohomology theory. So we can associate some H star of M phi M. So this is also called the cohomological Donaldson-Thomas invariant, or BPS cohomology. So we can associate such a one. So then the natural question is that whether we can have this picture. That is, the question is that whether there is some DG category which recovers this diagram. And in fact, and also I'd also want it to be category and also smooth and proper. I'm interested in this question because so this, if we can find such a smooth and proper DG category, it also produces some new examples of smooth and proper DG category, which are not, which gives certain some categorical resolution of singularities, which do not exist in the usual classical geometry. So anyways, the first question is that whether there is such a category. So this is an open problem, even if we don't have this. Even if we don't have this first as a first issue. So this is because this is relative to certain Green problem of the so-called matrix factorizations. And if we have also this first issue, then this is more the difficult question. So this is the first motivation, and yes, I'm going to give second motivation from the classical algebraic geometry. second motivation is singular homomorphic symplectic variety. Again, so let's take S to be a K3 surface and take V to be element of algebraic nuclear lattice. And as I said, so the moduli space of semistable objects. So this is a homomorphic symplectic if when V is primitive. But if this V is not primitive, so still there is some homomorphic symplectic structure on the smooth part, but usually, it always has some singularities. So this is singular homomorphic symplectic variety. And the people studying homomorphic symplectic manifold tried to construct new examples of homomorphic symplectic manifold by considering the resolution of singularities of such singular homomorphic symplectic varieties. So there is a famous example due to O'Grady of constructing such resolution. This is due to O'Grady. So there is some resolution of singularities, and in fact this is crepant resolution. And this is but this is only applied in the case that when the divisibility of V is 2, that is V is twice of square of some primitive, and V0 square equals to 2. And in fact, so this gives a new example. It gives a new example of homomorphic symplectic manifold, and this is 10-dimensional, and this is not deformation equivalent to the Hilbert scheme of 5 point. So this is called O'Grady's 10-dimensional example. So when O'Grady found this example, so the people tried to construct resolution of singularities in other cases, but it was later proven by Kaledin, Ren, and Solgar. In fact, so there is no crepant resolution in other cases. So there is no hope to give a new example of homomorphic symplectic manifold by taking the resolution of singularities of such singular symplectic varieties. But this is a result for in the classical algebraic geometry, and I'd like to see whether we can have some such a crepant resolution in some categorical sense. So the second question I'd like to address is that whether there is a crepant resolution of M in categorical sense. That is, we may try to look for some smooth and proper DG category, which may be regarded as somewhat resolution of singularities of these singular symplectic varieties. The reason I'm interested in this is that, I say that so this first question and second question are closely related. This is because, let's say, so far, so this is a case of K3 surface, but instead of K3 surface, let's consider the product that is K3 surface product affine line. So this is the total space of canonical line bundle on this K3 surface. So this is a non-compact Calabi-Yau threefold. But nevertheless, we can define the Donaldson-Thomas invariant or BPS invariant, and this is also known. So in fact, so this is equal to the minus of Euler characteristic of Hilbert scheme of point. So that holds for any V. So this was conjectured by myself many years ago, and also proven by Marek and Thomas. Using several techniques on emulative geometry. But so this is surprising from the geometry of the moduli space, because of course this is okay when V is primitive, because in this case the moduli space is deformation equivalent to this Hilbert scheme of points. But when V is not primitive, we cannot see any homomorphic symplectic manifold from this moduli space. So first, so in this case we have crepant resolutions, but this is not a deformation equivalent to this Hilbert scheme of points. Also, in other cases, so there is no crepant resolution. So a priori, so we cannot see any homomorphic symplectic manifold from the moduli space. So I have been wondering why this identity holds. So this is quite mysterious from the viewpoint of the geometry of the moduli space. And this is also some instance of the chi independence, which I mentioned in the first set in my first talk. So that is, for example, if you consider V, the Mukai vector is 0 beta chi, so then the right hand side is independent of chi. So this implies chi independence. So by combining these arguments, so the answer I'd like to propose is that. So this first question about the existence of some categorification of the Donaldson-Thomas invariant. So that is question 1 for the x equal K3 surface product affine line. Maybe question 2 about the categorical resolutions of this singular symplectic varieties. So this is the motivation of my talk, and now I'm going to state the main result. So this is, I'm talking about the so-called Quasi-BPS category, which answers to this question. So again, the setting is that S is now K3 surface. And the Mukai vector V is a multiple of some primitive 1. So this is primitive. And D is some positive integer. So then for this K3 surface, we can consider the similar diagram of the moduli space, which I have written before. That is, first I have this M. So this is moduli space of semistable objects on K3 surface. So this is singular homomorphic symplectic varieties. And so this is GIT quotient of some still singular everything stack. And this is embedded into some derived stack. So this is MSV. So I'd like to consider the derived category of coherent sheaves on this derived stack. So this may seem to be some theory for the surface case, but it also contains some information of the geometry of the moduli space on this non-compact Calabi-Yau threefold, which I explain later. But anyway, so I'm considering this derived category of this derived stack, and there are some structures. The first structure is so-called weight decomposition. That is dB of this derived stack. So this is trivially decomposed into the direct sum of the infinite number of direct sums. So that is this form. So roughly speaking, so at each point of this moduli stack, so there is some trivial automatism that is, it always admits some scalar automatisms. And this W means that, so this is C star weight equal W with respect to this scalar multiplication at each point of this moduli stack. So this is maybe seen as some trivial decomposition, but this is quite important in the categorification of Donaldson-Thomas invariant. And the second structure is so-called categorical whole product. That is, so I assumed that V is some multiple of this primitive Mukai vector. And let's take some decomposition of this D into k pieces, D1 plus 2 dk. So then we can consider some stack of the filtrations associated with this decomposition. That is MS V1 to Vk. So this is a derived stack of filtrations. Such that each associated group is again semistable, and it has Mukai vector equals to Di multiplied with V0. Again, so this is some nice derived stack, and we have various evaluation maps. MSDIV0. So this map is taking this filtration to the associated group. And also, we have a map from here to MSV that is sending this filtration to F. So the categorical whole product is given by just taking pull back and push forward of this diagram. The key point is that, so usually, so there are some issue of taking pull back and push forward, especially when the relevant varieties or stacks are singular. And in fact, so these are the singular stacks. So it is not obviously clear whether we can take its pull back and push forward. But nevertheless, we can do that in this case. So this is due to the work by Porter and Sara. So they considered more general case for the not necessary case surface. So anyway, so this case we can define the pull back push forward functor dB of ms div0 to dB of ms dv0. So this is regarded as certain associative product. So this is due to Porter and Sara. now I state my main result. For first main result. So this is a joint work with Toda Padua. So that there is some, so yeah, let's recall that V is given by d V0, and V0 is primitive, and let's write V0 square equal to 2g minus 2 for some integer g. And there is some subcategory Ts V in dB of ms V such that, so there is a semiorthogonal decomposition that is dB of ms V equals to Ts di V0 Wi plus minus 1 di. Okay, that's on I dj minus dj, where this the right hand side is after all the decomposition of this d into arbitrary decomposition, where each di is non-negative, and also we have this constraint. And also, so this is the restriction of the categorical whole product or the box product of these subcategories. And in fact, so this is free faithful. So this is regarded as some PBW decomposition of the category. And in the case of Bournemouth homology of this stack, there is a work by Davison and his collaborators giving such some similar decompositions with respect to the so-called BPS cohomologies. And in fact, so sorry, maybe I forgot to write W. And moreover, if so that this divisibility of V that is D and this weight W is coprime, then if we take topological case theory of this subcategory, and take its order characteristic, so then it equals to the minus of the BPS invariant. So that was equal to the order characteristic of Hilbert scheme of point. So that is false even if V is not primitive. So in this way, we can give some categorification of the BPS invariant when this D and W is coprime. So as a remark, so when D equals 1, that is a primitive case. So then this is indeed equal to this one. And when D is bigger than 1, so this subcategory is inductively determined by this semiorthogonal decomposition. So this is SOD, semiorthogonal decomposition. So although this is a theorem, so this also gives a definition of this subcategory by this semi-orthogonal decomposition. But there is also some description of this subcategory, and in fact, so this subcategory is closely related to the window category, which was mentioned by Kentaro yesterday. That is locally on this classical moduli space. So this category is in fact equivalent to the some window category inside of some matrix factorization category. So there are some data of this one, and this one is given by some weight condition, something similar to the window category. But there are some crucial difference. So one difference is that, so in Kentaro's talk yesterday, so if you take some generic stability, then this quotient was 21-fold stack. That is he said that the group G is reduced to some finite group. But in this situation, it never happens. So for any choice of stability, so this is not a 21-fold stack. So G cannot be reduced to the finite group. So for any choice of stability, this category is not equivalent to this one. In fact, this is smaller than this one. But nevertheless, if we define this category, and also this description is only local. So this description depends on the choice of the chart, which describes this moduli stack. But nevertheless, these locally defined window categories can be globally grouped to give a global subcategory. So this is somewhat more intrinsic one. So although locally, so this category is closely related to the window categories, its role is quite different. So anyway, so this first one gives the answer for the first question about categorification. So now I'm going to give its revision to the categorical resolution of singularities. So in order to state about this, we have to modify this derived stack. That is, so this derived stack has some extra obstruction space, and it corresponds to some one-dimensional direction of the second factor of the complex number C in this non-compact Calabi-Yau seafold. So I'd like to get rid of this extra derived structure. So that is, so there is some closed substack. So the reduced stack. That is, roughly speaking, the obstruction space of this moduli stack is x2 of the sheaf. And but so there are one-dimensional subspace of this obstruction space. And so this reduced stack is that obstruction space is given by the kernel of this trace map. So in fact, when this G is bigger than or equal to 2, then this reduced stack is nothing but the classical outing stack. So this is also due to Kaledin and then Suga. So this is something more close to the classical stack. But anyway, so on this, this is just get rid of the trivial derived structure, and we can also define something similar category, which I denote by dB of MSV reduced, but with weight of W. So if you look at this category in the primitive case, so this is reduced to a classical derived category. that is when d equal 1, then so this, so yes, for simplicity, I'd write this category just as, for simplicity, I just write it d t. So then this category t is nothing but dB of this MSV, but treated by some Brauer class. So that is when V is primitive. So this is again. So this is a holomorphic symplectic manifold. That is deformation equivalent to the Hilbert schema point. And this one is alpha is some Brauer class of this holomorphic symplectic manifold. And this means that this is a derived category of the alpha omega treated sheaves. So in particular, so this is very nice category that is in fact smooth and proper. So if you don't take this reduced one, we may have some extra derived structure which affect these properties. So in that case, the properness is does not hold. But if you take the reduced part, then it becomes proper. And in fact, so this is homomorphic symplectic manifold. So this is in fact Calabi-Yau category. So this means that the so-called self functor is trivial. Where the self functor is given by some functor which satisfies this functorial isomorphisms. Which plays a role of the self-duality. So the second statement is that, so this is a case of when D is one that is primitive case, that for the non-primitive case, we still have a similar statement. When D is bigger than 1, but again, so but this D and W is coprime case. Then this category T is, again, this is smooth and proper. And moreover, so if the category is smooth and proper, there is a self functor. And the self functor is, in fact, which we conjecture to be isomorphic to the shift functor, but we could only prove that this is the case et al. Locally on M. So there are some technical issues to give global statement, but we strongly believe that this holds globally. But anyway, so this shows that even if V is not primitive, this is a quite nice DG category, and we can regard it as a certain twisted version of categorical crepant resolution of this singular symplectic variety, and which is more close to the derived category of homomorphic symplectic manifold of K3 Hilbert schema point type. And in fact, we have conjecture that so this category is equivalent to the derived category of some treated homomorphic symplectic manifold. That is EB of n of beta homomorphic symplectic manifold. That is deformation equivalent to this Hilbert schema point and beta some Brauer class. But so this is coincide relative to the some kind of classical limit of the Lagrange duality, and if this is true, so this is some statement, not a local statement, if coming from this one, but this is somehow more a global statement. And so anyway, so I stop here. Thank you very much.
More how is this related to Langlands duality?
Yes, so we have some. So this is the case of KC surface, and we have something similar in the case of Higgs boundaries. And in the Higgs boundary case, we have we have some rank and Euler characteristic and weight. So this is the version in the case of Higgs boundaries, rank and Euler characteristic and weight. And we expect that we have this kind of duality in the Higgs boundary case. And this is the flip of the Euler characteristic and weight. And in fact, I think so in the classical limit of the geometric Lagrange, so Donaghy and Pantev conjectured that there is some equivalence between the derived category of the Higgs boundaries, which somehow permutes the tensor structures and Javi structures. And this parameter chi corresponds to the tensor and W corresponds to the Jav. So this is regarded as some version of the Donaghy-Pantev conjecture, but the original Donaghy-Pantev conjecture is some concerns about the derived category of the non-finite type stack. So this is quite huge and not manageable. But this category is somehow Calabi-Yau category of a smooth and proper category, and I think that this is more chance to prove it.
Sorry, but then what is the relation between Hitch modular
sorry, I forgot to say. So basically, so this one is that this one is difficult when R and K is not coprime. For example, let's say 0, let's say 1, okay. And let's say 1, 0. So this is nothing but the derived category of the Hitch moduli, stable Hitch moduli space. Okay. So this is symplectic. And this is something which I don't know.
Oh, I see.
So this is something like the similar phenomenon.
Okay, thank you.
This is some very broad question. So T gives the categorical crepant resolution. You say T gives categorical crepant.
Categorical.
Yes.
In some twisted sense. Twisted means that generically, so this is twisted by the Brauer class.
And one question is, are there any notion? So primitive case that is just symplectic.
Yeah.
Any categorical definition of symplectic?
Categorical definition of symplectic. So there is some definition by Ablav, but his definition is quite complicated and lots of conditions, and I think it is not clear whether our definition fits into his definition. For example, he requires the embedding of this category into some derived category of smooth projective variety. But so in my situation, so it's not clear whether this is satisfied or not. So yes, there is such a definition, but it's not clear about the relationship. Yeah.
So you say you talk on case surface.
Yes.
Is it something parallel or abelian surface?
Yes. For any case, Calabi-Yau category, I think more or less you can do something similar argument.
You use case only for categorical surface. So abelian surface.
Yeah, you can also do something similar. Yes.
And in that case, is there some notion fiber of algorithm?
Fiber of organism map. I think there should be, but I haven't thought about it. Yes.
Thank you very much.
Maybe today's schedule is rather tight, so if you have questions, ask speaker directly. let's thank speaker again. 45 and schedule.